Hello, assalamu alaikum. We're group 13 from section 4, CSE 427 lab, and I'm MD Shadikullah Chaudhary. And let's start with our project. The project focuses on patch-based satellite image classification using the Statlog dataset. Each sample represents a 3 by 3 pixel neighborhood with multispectral features. The goal is to classify land cover types using machine learning. Okay, so let's move to the dataset loading and description. The dataset contains numerical multispectral features extracted from the satellite imagery. Each data point corresponds to a local image patch, and the target variable represents land cover classes. Okay, so this is a tabular data and the first 10 head of the data. So as it is a multi-class classification problem, so we label our classes as 1, 2, 3, 4, 5, and 7. And here's the sample. Here's the number of samples of each feature contains. Okay, so as we can see here, the dataset is very clean, and there is fortunately no missing values, so we didn't have to drop any column or rows for this. Okay, so let's move to the EDA part right now. So the EDA shows class imbalance across land cover types. Feature statistics indicates different scales, which motivates feature scaling. No missing or invalid values were found. So yeah, so class imbalance exists, and this is the distribution of selected spectral features. And this is the feature correlation of first 12 features, and that's it. And this is something like absolute correlations, and this is the class-wise distribution of target levels of training set, obviously. So here we can see some sort of imbalances exist here. So it's obvious we need some tools to scale these features. To solve the class imbalances, we used SMOTE. Now the question arises, why SMOTE? So basically, the SMOTE we use because to address class imbalance, obviously, to address class imbalance, SMOTE was applied only to the training set. This improves minority class learning without causing data leakage. So this is where we applied SMOTE. So, and here you can see the values before balancing and after SMOTE. Okay, so another part is scaling and train and test split, actually. So the feature scaling was applied for distance based and gradient based models. The test set was kept untouched to ensure fair evolution. Now let's explore the models first. So we covered 5 models we applied, actually. So the first one is logistic regression, second one is KNN, and then we applied MLP neural network and XGBoost and LightGBM. So first 3 models was done by me, and the later 2 is done by my fellow teammate Mahir Afsan. So the logistic regression. So in logistic regression, we try to extract a good accuracy from the dataset. So logistic regression was used as a linear baseline. It achieved moderate accuracy, indicating the classes are not linearly separable. So here we can see how we applied logistic regression in our project. So let's go through these 5 cells, and here we can see that we achieved 84% accuracy in logistic regression, and this is the confusion matrix of logistic regression. In KNN, obviously the target was to extract better result than logistic regression. KNN improves performance by leveraging local similarity in feature space. Hyperparameter turning shows better results than the linear baseline. So let's go through these cells of KNN, and we tested the KNN for multiple K values. So here we can see the K9 is actually gives the best result, which is 88% here. And if we plot the K values, the accuracy versus K values, and we can see the K is equal to 9 gives the best result here. Okay, so MLP captures complex nonlinear relationships between spectral bonds and neighboring pixels. It outperformed KNN and logistic regression. So, so it was obvious that a neural network would perform better than logistic regression and KNN. So for this kind of dataset, obviously. So here we used activation function ReLU and solver Atom. So, and there was 2 hidden layer in our neural network, and if we go through this cell, and we can see that we achieved 89.5% accuracy on this, and this is the confusion matrix of MLP. So this is from my side, and the later part will be covered by my fellow teammate Mahir Afsan. Thank you so much.
Hello, Assalamu alaikum. My name is Mahir Mutasir Rafsan, and in my part of presentation, I will analyze and compare the XGBoost and LightGBM models used in our project, focusing on confusion matrices, ROC, AOC performance, and final conclusions. So why XGBoost and LightGBM? From our earlier experiments, traditional models such as logistic regression, KNN, and MLP showed decent performance, but they struggled with complex, nonlinear decision boundaries and imbalanced spectral classes. Therefore, we focus on gradient boosting ensemble models, especially XGBoost and LightGBM, because they handle feature collinearity well, they are robust to noise in satellite spectral data, and it perform well on tabular high-dimensional datasets like Landsat. So now I'll show my confusion matrix. So, so this is my LightGBM confusion matrix. So here we can see LightGBM achieved an overall test accuracy of 91.3%. From the confusion matrix and classification report, Class 1 soil type 1 was classified extremely well with 98.9% precision and 98.7% recall. Class 2 and 7 also showed very high precision and recall, meaning LightGBM learned their spectral patterns clearly. The main confusion occurred between class 3, 4, and 5, especially gray soil and damp gray soil, which have overlapping spectral signatures. Class 4 has comparatively lower recall, which confirms the spectral overlap limitations mentioned in our report. Despite this, the macro average precision was 90.36% and macro recall was 89.77%, showing strong class-wise balance after applying SMOTE. Now, I'll be showing my XGBoost confusion matrix. So in my XGBoost confusion matrix, we can see that XGBoost also achieved 91.3% accuracy, which matches LightGBM. So the key observations are XGBoost showed slightly more stable prediction across meiotic classes. Precision and recall values were very close to LightGBM with a weighted F1 score of 91.23%. Misclassifications followed the same pattern mainly between spectrally similar soil classes. This confirms that the errors are data-driven, not model-driven. In short, both models handled balanced classes very well, and confusion matrices clearly show that SMOTE successfully reduced majority class bias. Now I will show you the ROC curve and AOC analysis. So in this part, you can see that XGBoost achieved a macro average AOC of 0.991. This is significantly higher than baseline models such as logistic regression, which achieves 0.975. AOC close to 1 indicates excellent class separability. The ROC curve show that XGBoost maintains a high true positive rate even at a low false positive rates. LightGBM also demonstrated very strong ROC performance, closely matching XGBoost, which confirms that gradient boosting models are highly effective for multispectral Landsat classification. Now I will show my project report. So I will start in a minute. So firstly, here is my introductory part. So in the introductory part, I will say that satellite image classification plays a crucial role in Earth observation, especially for land use and land cover analysis. In this work, we focus on the Statlog Landsat satellite dataset, which contains multispectral information from 4 spectral bands collected over 3 into 3 pixel neighborhood, which results in 36 features per sample. However, classifying this data is challenging due to two main reasons. First, high correlation among spectral features, and secondly, severe class imbalance. To address these challenges, we designed a complete machine learning pipeline starting from data preprocessing and imbalance data handling and ending with a detailed comparison of multiple models. Then, in the second part, we wrote the literature review. In recent years, remote sensing research has shifted from traditional machine learning towards deep learning based approaches. Previous studies show that combining landscape matrices with object-based image analysis, or OBIA, improves classification accuracy by using spatial and geometric information beyond raw spectral values. Modified unit architectures have been highly effective in semantic segmentation tasks, including sediment monitoring in the Bengal Delta. To improve efficiency, MB unit, which uses mobile net encoders and depth-wise separable convolutions, which reduce parameters by around 35% while maintaining strong performance. Other research applied VGG16 and DeepLab V3 Plus for agricultural monitoring by isolating farm regions and segmenting pixels accurately. Comparative studies reveal that UNet consistency outperforms PSPNet, and accuracy can be further improved using edge-guided networks such as HFCN. Multimodal models like FMFA, FUNet combine optical and SAR data using wavelet transforms, improving robustness. Despite these advantages, a major limitation remains the lack of label data, encouraging future research in semi-supervised learning. And then comes our third part, which is methodology. So here are two parts. The first one is data preprocessing. So our dataset contains 36,435 samples. We applied standardization using standard scaler, ensuring all 36 features have zero mean and unit variance. This step is essential for distance-based and gradient-based algorithms. Secondly, imbalance mitigation using SMOTE. Initially, the dataset was heavily biased towards class 1. To solve this, we applied SMOTE, or synthetic majority over sampling technique. We generated synthetic samples from minority classes. After SMOTE, each class contained exactly 1072 samples, creating a fully balanced dataset. Here in this graph, we can see the balanced dataset after using SMOTE and the previous imbalanced dataset. The blue ones and the red ones are after using SMOTE. Then my algorithm approach. So in my algorithm approach, we can see that we use 5 different machine learning models covering a wide range of learning paradigms. Logistic regression was used as a baseline. It is a multinomial softmax based linear model optimized using the LB-FGS solver. Then KNN. It is a distance-based non-parametric model. We used Euclidean distance with distance weighting after tuning. K equal to 9 provided the best variance trade-off. Then comes MLP. MLP consisted of hidden layers with 64 and 32 neurons using relay activation and Adam optimizer. Dropout was applied to prevent overfitting. Then comes XGBoost. XGBoost is a powerful gradient boosting ensemble model. It optimizes loss using Taylor expansion and includes L1 and L2 regularization. Its its sparsity-aware split finding is especially effective for satellite data. Then comes LightGBM. LightGBM uses a leaf-wise tree growth strategy. It applies gradient-based one-side sampling and exclusive feature bundling, making it faster and more memory efficient while achieving high accuracy. So here is my result and comparison part. So this part clearly shows that the ensemble models outperform traditional approaches. Both XGBoost and LightGBM achieved the highest test accuracy of 91.3%, while logistic regression and KNN performed comparatively lower. A macro average precision and recall also confirm the consistency and stability of gradient boosting models. The ROC-AOC analysis further highlights the performance. So the next part is the limitations, restrictions, and future work of our project. Despite strong performance, there are some limitations. The spectral signatures of damp gray soil and gray soil overlap, making them difficult to separate. The dataset lacks temporal information, preventing seasonal land covering analysis. Additionally, SMOTE increases training time, especially for ensemble models. So for future work, we aim to integrate convolutional neural networks and explore multimodal data fusion, combining optical and SAR imagery. This can reduce reliance on label data and improve generalization. So to conclude, I would like to say classifying multispectral Landsat imagery is challenging due to feature collinearity and class imbalance. Our study demonstrates that ensemble boosting methods, especially XGBoost and LightGBM, significantly outperform linear and distance-based models. The use of SMOTE proved essential in balancing recall across all classes, achieving 91.3% accuracy, and 0.991 AUC confirms that these models can learn complex nonlinear decision boundaries. This work provides a robust and scalable framework for automated land cover classification and highlights the importance of efficient ensemble models for real-time environmental monitoring, particularly in regions like the Bengal Delta. Thank you so much.